Hi, my name's Yusuf, and this is Lab 2, Motion of a Falling Object. Introduction. The purpose of this lab is to analyze the motion of an object that has dropped from rest and falls slowly. We will explore the concept of terminal velocity and how it relates to the drag force acting on the object. We aim to investigate the effects of gravity alone versus the combined effects of gravity and air drag on the object's motion. Two computational models will be developed, one that accounts for only gravity and one that accounts for both gravity and drag, where drag is proportional to the square of the object's velocity. The observed motion from a recorded video will be compared with the predicted motion from both models. The models of the object falling under the influence of gravity and drag used in this experiment are based on Newton's second law of motion, also known as the momentum principle, which states that the change in momentum of an object is proportional to the net force acting on it and the time that the force is acting. In both models, the object's momentum and thus velocity changes as there's a net force applied. In the gravity model, this net force is gravity, while in the drag model, this net force is composed of both gravity and drag. The model that includes air drag predicts the object will reach a terminal velocity, where the drag force balances the gravitational force, causing the object to fall at a constant speed. Alternatively, the gravity-only model shows continuous acceleration without any limiting speed. We observed that the inclusion of drag significantly improves the accuracy of the predictions. Here's the experiment. Our system was a paper ball, and the surroundings were the earth and the air. The paper ball was dropped from a height 1 meter above the ground, and its initial velocity was at 0 meters per second, since it starts at rest. The ball was dropped and observed until it hit the ground. The position at different periods of time was recorded and plotted using tracker. Here is our code. Up here, we initialize the ball, we initialize the trail, we initialize the origin. We then create some arrows to represent vector quantities, and we initialize the graphs and their axis titles. Then we initialize the ball's mass, in this case it's 1 kilogram, and we initialize the ball's initial position, which we do as 0, 1, 0, so it's 1 meter high in the y direction, and the velocity starts at 0 in all dimensions. Here is the initial time, and here is the time intervals at which we want to record data. Here's the magnitude of acceleration due to gravity, which is 9.8 since we are on Earth. And here's a unit vector for the positive y-axis, which we call j hat. As you can see, it only has one component, which is the y, and it points, and it's a value of 1. And here's a proportionality constant for the magnitude of the drag force. Since this model is only accounting for gravity, we do not have any value for the proportionality constant, so this remains 0. So our loop runs for as long as the ball's position is greater than or equal to 0, which means it will stop once the ball hits the ground. This controls how fast the program will run, and this is our net force, which is simply the negative the ball's mass times gravity, and there's only a net force in the y direction since there are no x or z forces acting on it. And then we update our ball's velocity by adding the velocity to its acceleration times time, the velocity update formula. And over here, we update the ball's position using the position update formula by adding it to its velocity times the change in time. We then advance the clock by adding the time elapsed, and then we print the graph. Now for our model with drag, there are only some slight changes, such as the proportionality constant is added. We give it a value of 1. And over here for our net force, we, instead of only using gravity, we add drag to the equation as well. So since the velocity is only acting in the y direction, we don't need to worry about the x and z directions. So we can let our vector for drag equal to 0. Then in the y direction, b times velocity in the y direction squared, and then another 0. We add both of these up to get the total net force acting on the ball at any given instant. And we update the velocity, update the position the same ways, and we graph everything the same ways. Here are our models. This is a model with only gravity. As you can see, the slope gets steeper and steeper throughout the entire time. Here was a model with drag. As you can see, it gets steeper and steeper initially, but then it stops changing. Then it becomes a straight linear line. Our observed data follows closely similar to that. It starts off by changing its slope, and then it becomes almost the same. Here's a comparison of all the models. As you can see, the actual observed data matches closely with the simulated data with drag, and is completely different from the gravity simulation, which ends much earlier than the other two. So what are some sources of error? The main error in this lab is the discrepancy between the predicted motion from the drag and the observed data. The actual data showed that the terminal velocity was reached a lot earlier than expected. The difference is most likely due to estimations of the mass of the object and the proportionality constant B used in the drag equation. The proportionality constant depends on factors like the shape, surface area, and density, which are assumed rather than calculated from direct measurements. These values were not measured precisely, leading to small inaccuracies. Also, minor variations in the object's orientation or air turbulence during the fall could have introduced unaccounted variables affecting the drag. Here's conclusion questions. The model with the drag predicts that the object will eventually reach a terminal velocity where the drag force opposing the motion increases with speed until it equals the force of gravity. Once the terminal velocity is reached, the net force on the object becomes 0 because upward drag force exactly balances the downward gravitational drag force. This means that after reaching terminal velocity, the object falls at constant speed with no further acceleration. If the object is initially thrown downward, the terminal velocity will be the same as when the object is from rest. However, as shown on the left, the object thrown downward will reach terminal velocity faster because it starts with a higher initial speed, as you see with the slope starts off high. The object is thrown downward faster than the terminal velocity. The object's velocity will initially decrease as the drag force becomes larger than the gravitational force. Over time, this object speed will decrease and eventually stabilize at the terminal velocity where the drag force and gravitational force balance out. The terminal velocity will be reached in all cases. Thank you.